The following presentation was recorded at the 2014 SouthEast LinuxFest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information, visit www.southeastlinuxfest.org. The SouthEast LinuxFest would like to thank the following diamond sponsors in 2014 for helping make these videos possible.
Okay, so you guys are like the hardcore LinuxFest people, so that it would actually show up at the 9 o'clock Sunday slot. So, and we have another one, so yay. So if you made it out, you know, God bless you. Thanks for coming out this morning. Yes, I know. So if I can stay awake, maybe you have a chance. So, okay, so so who am I, briefly? So I am a software engineer for this outfit called Alert Logic. I live in Houston. My background is primarily in systems programming and native code with C. Actually went to Erlang Factory this past event they had. They had their own conference, and that was kind of my presentation, was from the perspective of someone coming from that background to this background, and it's different, and so that gives me a unique angle, I suppose, in some. Okay, so we'll just kind of jump in here and raise your hand if you got a question in time. So okay, let's just kind of scope Erlang a little bit. So it does, it's a virtual machine architecture, but you do compile things to bytecode, so at least you get the benefits of, and it's better now than it has been in the past, but some static analysis on the input side. You do have dynamic typing, which, depending on how you're looking at things, is a pro or a con. It's a functional programming paradigm, which is the most difficult for me, and most difficult for people who are probably not coming from that. We'll talk about that. You have really outstanding pattern matching facilities, which is a big plus. And we can talk about that a little bit. And what makes this special, makes it a little bit different than other functional programming environments, is the unified I/O and concurrency and distribution model that it gives you. And it also has an interactive console like, you know, Python or several other things. And then I like to think of it as this idea of an entire simplified operating system that you can use as a library in your application. So your end result of what it is you're doing is not so much an individual program, but it is a system of multiple programs that function as a whole, which you do anyway, but this is on a little bit different take on it. So Erlang originally is from Ericsson. This goes back to the 80s. They used it in-house. It was a experimental proof of concept. It had its own neglect. Finally came out in open source world. It's used all over the place. In a lot of places it's big. It's got a big industrial following, more in Europe than in North America, but it's a cool thing. It's kind of nice to see how it's kind of an obscure one. People don't notice much, but it's gotten a resurgence. It's kind of a renaissance, but it's still very much alive and well. So if you take anything out of this, you need to go watch this YouTube video, which will pretty much leave you incapacitated with laughter unless you just don't get anything. So just go YouTube this sometime. This guy made this kind of as a joke promotional video for Erlang, trying to kind of make fun of how 80s it is and try to give it a modern take. And he makes fun of Node.js and Ruby and all, so it's just hysterical. So has zero technical, benefit to watching that, but you just have to. That should give you all the background information you need. So probably the two in the open source universe, big examples that we think of that are getting a lot of attention for Erlang lately, and you have outfits that would otherwise never even consider Erlang. They're having people kind of learn it and use it for these two things. RabbitMQ is a generic message passing bus framework, and if you know Erlang, you can have an additional level of customization with it, and it's just an example of an amazing generic component that you can build with it. And then Ryak is distributed database system. It's a NoSQL front, and it's one of the cool things about it that's a little bit different is the geographic dispersion concept. So that actually you can have network splits and things like that. So that's kind of its, in my mind, its unique attribute. But that's all built with Erlang on the top layer. Has obviously both these things have other components besides. So let's talk about some, pros. Okay, like I said, this is time tested, and by that I mean the code base is been tested for a long time, but the paradigms and the models that it uses have been exercised over time. So a lot of the original ideas have been let go, and many of the core ones that actually are great have been held on to. It's just a rock solid thing. It's just been around for, if you think of an example like Unix, been around for a long time. Even though it's different, we get the ideas, we get the concepts that they work very good. You can do rapid. It's a great way to explore ideas, prototype things, make production systems quickly. It's a high level tool, but a very powerful one. Compared to many things, and depending on what you're talking about, the performance is outstanding. One of the reasons to use it is excellent performance characteristics, especially with parallelism. If you watch the video, you'll get the joke about get the girls, get the boys. It's also very different. I put that as a pro because it actually was here. It was at the SouthEast LinuxFest in Spartanburg a couple of I watched a great presentation. The guy was talking about don't stagnate. If you work on the same thing for 10 years or longer, you get really good at that. But it also limits you and inhibits you from other growth that you otherwise might not have. And so, try things that are different, explore them, play with them, and even if you don't fully go on board or fully use them, it will help you to expand your mind and expand the way you look at things, and the tools that you normally use and you think that you understand very well, you'll look at them with a new perspective. So it's very good. And portability. So that's less of a concern now, but it is possible to run this on a variety of operating systems and architectures. So historically that made it more a big deal. On the cons, I put some of the same exact ones. The portability is a negative in the sense that there are some things that could be done in a more Linux way, but that abstracting especially things like threading models, console I/O, stuff like that. But still, it's cool. And the very different is also a problem in the sense that it's just different. It's weird, at least for me. Obviously, there are performance downsides both to virtual machine and to functional programming in general. Don't kill me if you're a big functional programmer. And the syntax is bad. So to give you an example, you can terminate a line 4 different ways. You can terminate it with a space, with a period, with a comma, or a semicolon. And you have to use the right one depending on the context. So like if you go in there and you say, I want to tweak this a little bit, let me just insert a line or text it, you go, and so the line above it, the line you just added, and the one that below it now probably has to have all the termination changed, just things like that. Okay, so like I said, the original use case was with Ericsson, and they were making telecom switches, which is a heavily I/O intensive environment, and so one of the whole reasons to use Erlang and consider it is for I/O applications. So it's worth taking a step back and taking a little bit of an overview of what we mean by I/O. We won't harp on this forever, but just to consider it for a second, at the lowest level, the way things mostly work now is you have your core CPU with your registers and stuff, and then at this level, I/O means anything going in and out of that core. So anytime you write in instructions to fetch things out of RAM, set things in RAM, that's an I/O operation. And all real I/O, in other words, device I/O, is actually just mapped into memory address regions. So you have this abstraction to where at a certain level, all you're ever doing is just fetching and setting, doing assignments from memory addresses. And then the other big component of that is you have an interrupt model, which is obviously how you tell it when it is that you need to handle the different external stimulus and internal stimulus. Okay, so what that gives you is that gives you a means to abstract I/O to the point where you can say, regardless of what kind of I/O it is, we can handle it in the same path. So what are some ways that people have handled concurrent I/O? Concurrent meaning you've got more than one source of something. So I don't know if I was actually did another presentation on Friday about historical systems, which is another fascination of mine. And one of the things that came up in that research that applies to this is this monotonic concept. So some of the original time-sharing systems, some of the original mainframe systems, they worked simply by saying they had a fixed amount of time, and you would rotate for intervals around, and if you used it all, great. If you didn't use it all, that's okay. It would just, there was no extra logic of when to go to another thing. You just had a finite amount of time shuffled around. There's actually still some systems that work like that today. Excuse me. So another one is there are systems, older ones, that have I/O done with completely different hardware, so that you can, that mainly comes from mainframe world, where you say, okay, we'll take all our terminal I/O, that's in a whole separate subsystem, and then we batch that out to actual core. But there is still signal-based I/O in Linux. I guess more in the, if you imagine from a Windows background, they would call it overlapped I/O. That's kind of another one, but it's not really relevant to where you're just pointing out that it exists. You can also just have traditional multiprocess, in the sense that we'll have a single process that's just handling one piece of I/O, blocking on that, and we'll multiplex that whole concept with the OS, and then we can say multi-threaded. Now put that on there because sadly, the way that a lot of things worked out, you had this situation where we were doing multi-threaded programming explicitly to handle I/O, which is really disappointing because that's a terrible way to have to handle I/O. Multi-threading in the abstract has some advantages for certain problems, but just to solve I/O is, I think, sad. And multiplex, meaning, so we'll say we'll use a select or a poll or something like that. So we'll have, you can say, I have X number of I/O stimulus. Let me know if any of those can be operated upon. And what you see is the efficiency point is when you actually use a combination of multiprocess, multi-thread, which could be the same thing depending on what environment you're on, and then multiplexing those within this. So each thread handles a certain number of I/O jobs that are multiplexed, which is the Erlang model. That's what it gives you for free if you're using it. Okay, so then you also have this other concept of we're not necessarily trying to do concurrent I/O jobs, although we might, and we're not necessarily trying to do parallel processing, although we might, but we still have just different narratives with our logic. We're trying to solve this problem over here, and we're also trying to solve this problem over here, and these things have to be thought about at the same time. So, traditionally you have, like in a C background, usually what you're doing is state switching of some kind. We have some kind of context, we save information to that, and as we go to different jobs, we go back to that. That's also what happens at the OS level. Or again, you can say you can just split the problem out in entirely separate programs, chain them together somehow. You can use pipes, whatever, or you just actually have a true multiprocess system. Again, the multi-threaded explicitly for logic makes a little more sense, a little more justifiable. The historic one that is I think really the superior model in a lot of ways is the coroutine concept, where you're not actually doing things in parallel at runtime, but the logic is parallel. You can manually switch between contexts without all the manual saving of state. That is what Erlang gives you for free. And then another model would be you could say that things like we'll service one request, and that request is stateless and move on to another, like you see in like web server logic sometimes. You could say that's another paradigm. Okay, then the other concept is, well, we're not just trying to handle multiple I/O, and we're not just trying to handle multiple narratives of logic. We also actually have parallel processing hardware of different kinds, and we want to find some way to leverage that. So Okay, you've got vector operations, as in I've got a single operation that I want to perform on multiple units of data, like a GPU. Erlang is not going to help you with that. That would be an example of you want to go back to native code. Another one that's odd, that kind of comes up in conversation, I think is fascinating, is I'll call it optimistic branch prediction, in the sense that in any kind of pipeline processor, one of the tricks it's doing now to try to make things go faster is you have a branch and conditional. You'll have an if statement, and the processor can say, I don't know which code path is going to be taken because we don't know what the value of that conditional is yet. But what I can do is I can either just pick one that I think it's going to be, or go ahead and run both of them at the same time. And then later on, when we figure out which code path needs to be run, we'll just kill the other one. And this all happens behind the scenes, but okay, so that's more of a hardware discussion, except for the fact that you had the whole Itanium thing where part of that model was to expose that to the programmer. And you actually were supposed to put these branch prediction hints, which you still have, but they're not used as much, to actually say, this is what I think you're supposed to do. And that model didn't pan out so well. Another one, like OpenMP, would be an example, I think, of annotated code sections, where you take a just serialized linear program, but then you take one specific part, like a loop, and you say, okay, we can parallelize this. And it's kind of a retrofit technique, but that's another good one. Then you can have the more traditional approach, or what we call traditional now, where you actually just do atomic commits to memory. You have locks and things like that, and what amounts to threaded programming. And then the other model is just send I/O between programs or between program units, or message passing, like MPI, or a message bus like the RabbitMQ, something like that. That's the Erlang model. That's what Erlang is giving you. It's based on message passing. Okay, then you went further and you say, okay, well now we actually want to throw more than one box at the problem. So either because we want failover, or either because we want to have capability to do more processing. Batch farm, get the idea. That can be fine grained. It can be coarse grained. You can say we have a lot of work to do. Let's farm it out to different servers. It's still used. That's the original approach. NUMA is, I guess, the more prominent example we see now would be the Oracle Enterprise notion. That's where you actually can do a memory mapping onto remote machines, kind of thing. And then, of course, message passing. MPI being probably the more famous example, but or you can just write sockets, do it yourself. But that's what Erlang gives you. So that's also the Erlang model. So so you have this unified model of solving kind of all these problems in the same way. So you have a nice range to work with. All right, so hello world, okay? So there is a one-to-one relationship between source files and modules in Erlang. So your Erlang source file is always going to say module and then what the name of it is. Then you have to explicitly say the functions within that module that you export. Or you can actually say, don't do that. I'm going to be lazy and sloppy and export everything. Don't do that. And then you define your functions. In this case, we just have hello world. The way that this actually is working is we are saying the process that runs this, send a message to our console process, or the process that's handling I/O, and send this message. Which the system I/O process ends up being the console, and then you get this message. So let's take a look at, if I can hit the right button here. That's sad. We'll try again. Escape, maybe? Seriously? Okay. Go back. There we go. No telling what happened. Okay, so let's kill this. So, oh wait, I don't want to kill that. Okay, let's go back to here. I'm sorry? Yes, okay. Anybody know what that keyboard shortcut is in GNOME Terminal that zooms in on your text? Otherwise I can just do this. Control Shift. Ah, there we go. That's cool. This is, I had to set this laptop up pretty quick to get this. Okay, so we'll just close out of that. All right, so what we've got the that hello program in a file. So when this, so a lot of the examples and tutorials I give you are entirely based inside the Erlang console, which is what you need to learn. But I think it's hard. I would have rather, when I was first learning, to have someone show me this. So we're back in the real world of Linux, right? We're doing real development, right? We have text files that we can do version control on, and then we do regular development type stuff. Like we have a compiler, and we can say, here is the name of our source, right? And then the output on that is it created this file called a beam file. And beam is actually the initials of the engineers that came up with the runtime engine. So that's what that is. So now what we can do is we can run this thing. So we can actually come in here, and this is a little, if we were to run it in the console like we think of a regular program, it's a little bit awkward. That's why they don't show you first, but I think they should show you first, so I'm going to do that. You can say this, and you can say, if I can remember this off the top of my head. So what that is the, I'm asking it to start, and I'm giving it the module name, function name. We can talk about this other part later. And that's what we got to the console. So one of the reasons that was a little bit strange, because the default behavior is to start this virtual machine and spawn up all these other background processes within this virtual machine. So it's a multi-process virtual machine that are geared to spin up to do all kinds of cool stuff, which we don't do because we're just printing out hello world. And so we've manually specified that I want to run this module, this function, and then I want another module in this function. In this case, this module controls startup and shutdown, and we're just asking it to stop. So that's how we made it actually turn itself off after we run that. And then the no shell thing is normally, if you run it like this, we're going to be in an interactive Erlang console, which we didn't want to do in this case. We actually wanted to demonstrate that the I/O can be routed out to the real system and use it in the way that you think of as real programs. So like the traditional way that somebody would show you that is just bring up their Erlang console. You actually can do the compilation inside the console, but that's confusing because you still want traditional regular compile, like we actually call the compiler, because I can still put that in a make file, a script, regular normal stuff. But whatever. So we can call the module name and the function name. Well, if I can type on the, yeah. Okay. So so we can go one further. We can say this. We can do this with two connections, two remote connections. So let's say that we start with the Erlang virtual machine, and we want to enable the networking capabilities. So you can do long names, short names. We'll give it a short name. We'll call this top because it's the window on top. Come down here. We'll close this. I will start another Erlang process. We'll call this one the bottom because it's on the bottom. Now, normally on one single compute node, you would just run one instance of Erlang. So we can just imagine that these are on different computers, but it works the same way. Sometimes there's reasons to do this sort of thing. You can mix and match, do whatever you want. So we can actually go in here and we can say, I think I have it sheeted. If I just scroll up somewhere, make sure I type it in the right way. Yeah. So you can go to this RPC module. This is one way of doing things. And I can say, hey, what I'd like to do is I want to call, and I can give it, this is the name of another node. I want you to go to this module, this function with these function parameters, run that, and redirect the output back here, which is what they did. So in this case, the reason why we say the hello world still here is because it actually ran inside the VM running down here, but the console I/O was set up to go to here by default because it figured out where we were coming from. Okay, now if I can go to back here. All right, so yeah, as I was alluding to, so you still have a regular operating system, in this case Linux, and there are regular operating system processes that are going on. The entire Erlang virtual machine is a single regular operating system process. It doesn't have to be. It actually, there are implementations of it where it is its own operating system. That was the original use, was it would be the firmware on a switch. That stuff still happens. There are projects to run natively on Zen, for example, so we can strip out stuff and do something like that, but then you lose the leverage to mix and match regular Linux with Erlang, so. But that's there. And then inside that world that the virtual machine gives you, it has its own processes, which can also be called actors. So if you want to disambiguate the notion between a process that's inside the Erlang VM and when it's outside, you can use the word actor. Although sometimes people don't say that, and it gets confusing. We say processes. Well, what are you talking about? And these are they're implemented as coroutines in the sense that they each have their own. They're actually not using the stack hardware for the system. So you can actually have literally hundreds and hundreds of thousands of processes inside here, and you're not overflowing the stack. You're not having to do manual stack switching of any kind. It's just the way the VM implements it. And so in this case, the other thing about the model is the way that you can expose I/O to the outside world is you have these port actors. And I probably should have drawn a line, but so in this case, the other external process we have would be the one that was running bash in the console, and there's pipes that connect that back to the Erlang beam, and then inside there, when we, for example, we sent the hello world message, we're actually sending that over to another actor inside the VM and said, okay, you do something with this, and it knows what it's supposed to do, which is to send it back out to the outside world. So that is kind of the model for how you can connect to the other things. And then also we had the interactive shell that we're looking at was running there also. Okay, so now more about like what is the actual programming like. So with functional programming, there's this notion of immutable data. Does that everyone know what that is? Is it totally new to everybody? Is everybody okay? So, depending on your background, you love that and you think it's a fanatic. You're fanatic about it, or you despise it, think it's the stupidest thing ever. I still think it's the stupidest thing ever, but I will concede that there actually is a number of problems where that's the appropriate way to solve them. I didn't really understand what those problems were until I had started learning this, and many of them I still don't. But anyway, the point is that when you do a variable assignment, like let's say we take A and then we assign it 5, okay, that is now fixed at 5, and we want to reassign it to something else, and it's going to say, you can't do that. So that's cute and all. I mean, that's sort of the semantics we get from math. But how do you write a program to do anything like that? How could you conceivably do anything? So if you think about it for a little while, there actually is no answer to that. So you cheat. So that's not really the full story. So first of all, those assignments are on a per function, per process basis. So every time you run that function again, you can give new values to those variables. And in the Erlang world, where you actually have multiple processes, that also part of the reason why you have that is to kind of mitigate that also. So I can be running the same function multiple times in different processes, and those local variables can be whatever they want. And the other one is that there's use linked lists heavily in the functional programming world in general, but Erlang also. So here we make a list, we'll call it C. We'll give it 3 integers, 1, 6, 15, and we can, I probably should have shown full list manipulation, but you can dissect that list easily. So there's operators built into the syntax of the language to say things like, just give me a portion of this. So in this case, we're having the variable D. We want that to be assigned just to the head of the list, and it just 1. So you can do these concepts of rearranging list elements to kind of give some of the ways that you would have of reassign data. But for the most part, you just call another function. We'll talk about that in the next slide. The other thing we see here is that underscore. that's an example of pattern matching. So the pattern matching thing is kind of almost like the way you would think of, or way I would think of as a preprocessor macro logic, but it's done at runtime. So it's fascinating. It can do some really cool stuff. And the underscore is sort of a special pattern match. It means anything. It's like the wild card, the glob operator. You know, think of it as a star or something. So, but the better way that you would actually solve these problems is when you call the functions over and over again, you have to introduce this discussion. So in normal recursive function calls, like let's take on the left there, we've got a C function, and we do something pointless. We will just recursively call ourselves over and over and over again, adding 1 to this value until that value is 100, and then we collapse the recursion stack. So what happens here is every single time that you do this, we're creating a separate storage location for that variable A on the stack. And so when you learn this kind of stuff, you learn don't do that. You can have a stack overflow. It will eventually just collapse, plus you're just wasting memory. You have to have some means of controlling this and be careful about it. Now, if you are in assembly language, one of the tricks that you can do is you can say, all right, we want to call the same function that we're in right now recursively, but we want to call it in a different way. We actually don't need to maintain a separate copy of these local variables. We just want to update the value of the local variable and then enter into ourselves again. And they call that tail recursion. And some languages natively support this. In the example here we have C. Depending on the compiler implementation and optimizations, it is probably smart enough to do that for you in this function, because there's no real purpose of having a separate copy of the value A each time this is run. So it might be smart enough to do that. In the case of Erlang, I kind of think it would be probably better if there was a way to explicitly say that that's what you're doing, but you can have both ways. So because we're not calling it, and we haven't designed this function in such a way that you actually would have to have a separate copy of A, it automatically does this. And this is built into the language as a means of working around that paradigm that you can't reassign a value A. So just like in math, we can call a function as many times as we want to with different unique parameters. And it should get the same thing each time you call the same parameter, but each invocation of it is separately. So that's where that model comes from. You don't use, there is an if in Erlang, but you pretty much don't ever use it because it's strange and it's kind of not the way they want you to do things. You end up using a switch case, which they call a case block over and over again. So in this case, we're saying another example of pattern matching. So what this does is it says, all right, in our function, we're gonna do a switch case of A, and the first one we have is anytime A is less than 100, then we will recursively call it into ourselves, add 1 to it, and then the bottom pattern match. So we have both of the two statements, the two cases that it could be are both pattern matched on the wildcard meaning anything, but the first one has the when and the A is less than, it's called a guard. So you can just add these other expressions to sort of say, all right, only go in here. So it's different than saying if, or just, you know, so, but whatever, that's the way they do it. Okay, yeah. Oh, so the other thing that you have to deal with is there's no like while loops and for loops. So you say, well, how do you do anything again? And the answer is the same model. You do that tail recursion model. So if you're iterating over an array or a list, whereas, you know, in a imperative program paradigm, you would do some kind of iteration loop. And this, you're just going to do those tail recursive calls over and over again. But the other one that you have that it also gives you a way to do what amounts to looping is a list comprehension. List comprehension is sort of an amalgam of these linked list in syntax operations mixed with the pattern matching facilities. So an example right here is we have a list 1, 2, 3, 4, and what we're saying by that double pipe operator is what we're going to do is we want to take each element that's in that list represented as X, and then we want to perform an operation on it. In this case, we're going to take X times X, and we're going to create a new list from that. So this has the same effect of iterating over a loop, and you can actually do things like call functions in here and other kinds of complex stuff, but we end up with a list of squares. So those are the kind of the model for how you get around immutable data. All right, so let's actually look at something else. So the way that in the Erlang world, okay, the way that their message passing and the multiprocess works is really 3 low-level concepts. One is the spawn operator, and where you actually can create new processes, actors. The other one is this receive block concept, which is similar to the case, which you're saying, okay, when I receive a message, what do I want to do? Which messages specifically do I want to handle, and what can I do with them? And then you have this exclamation point operator, which is a way to say send a message to something. So let's take a look at what did I hit last time to make this work. All right, so this is a little program right here. Again, we start with the module name and definition. We'll just call it MP1 for message pass 1. And so this is a very primitive server. We'll call it an echo server. So we'll take our messages that we receive and we'll send them back to whoever sent them to us. And we'll put also some trace debugging messages in here so we can illustrate what's happening. So there's this function called self, which says what is the process identifier of the program we're running right now, and we can use that. So then we have our receive block, which says, okay, wait, basically block for a message. When we receive a message, try to do a pattern match on these outputs. So the first one we could say, if I'm literally sending it what they call these atom, which is a string that gets hash mapped back to an integer. So if it matches that, just send out this message and don't do anything else. And by not doing anything else, that means that this function is finished. And when this function is finished, that was what this process was running, so the process itself expires. The other thing we could do is if I'm sent a tuple, just like tuples in Python, where I want the 2 variables. One of them will be the from address of the process that sent this to me, and another one will be, so the generic word for variables in Erlang is terms. These are Erlang terms. Send me something, and I'm going to send it back. And I'll do my IO format saying, okay, I got to here. Somebody sent me a message. This is the message. We'll just print that out. And then we'll actually send it back to them. So we'll take the process identifier of who sent it to us, we use the exclamation point operator, and then we send back to them what they just sent us. And then we're going to use the tail recursion to enter in this loop all over again. So we repeat the process. So it's effectively like having a while forever loop. But you would, in other languages, if you did this, you would be built accumulating stack forever, but you're not here. And then we'll just have a catch-all that says, all right, something didn't work out. So let's actually try to run this, see what happens real quick. So we can go back, start our 2 processes again, or start our two VMs, and we can demonstrate that self thing. So that's our process identifier for wow, okay. For ourselves, so let's try to move quick. So let's make a variable, PID equal, it'll do a spawn, and we will say the name of the module, and we will say the name of the function, and we'll say the parameters, and bam. So what this is this is the return value of the spawn command, which is the PID of the new one. And this is the message from inside there. So we want to send it a message. We can say PID, we're going to send you a message. We'll give it something like hello. And so what we see here was, oh, I called it wrong, because what we were actually supposed to do is we were supposed to send it a tuple containing a payload and our process identifier for who we were calling it from. So that should work. So what we see here is this is the debug message from the program. This is the return value for this function call, which is going to be this tuple here. And this is the debug value. Did it get to the top of the loop again? So we say, where did the actual message go? So you can use this to diagnose things or just play with things in the console. You can use this thing called flush, and this shows the backlog of messages that are in my inbox message queue. So that's where that goes. Okay, so we have less time than I imagined we would, so I will normally you can never touch time, so we'll go back to this and we'll come back. So, all right. Now, so if you're doing, well, what I was going to show you in that last demo, but I raced through it too quickly, was actually do that same exact operation between the two processes. We can still come back and do that. But the point is that there's still ways of doing regular sockets programming. There's ways of doing HTTP endpoints. You don't have to, you're not limited to just a distribution protocol, but there's advantages, there's pros and cons to that too. Another concept we have of closures. This is another functional programming paradigm that you see in a lot of languages. And basically the idea here is we'll say, okay, we can have another function, we'll call this the takes a function, that you give the function as a parameter another function to run. And then beyond that, well, which you can, so basically like a function pointer, but what's even cooler is that the functions that we can give it are these nested functions inside other functions that have scope through local variables in the parent function. So for example, what ends up happening is you call this thing and you get the answer of 17. I'll put these slides on the thing. You can work through yourself. But the way that would work is we end up here and we say function of function. And initial C value was 5, but then this local variable that we had the entire time was 1 to the side. So that's why you get 17. So that was like the simplest example I came with. And sorry to pick up the pace a little bit, but we're trying to get there. And so if you look at like an analogy in a imperative programming language, back in C, because again, C rules the world, and that's the way God made it. So you can look at, this would just be the same thing with function pointers. Now, yes, you can use a global variables, but you don't want to do that. So you end up doing it more modern style, where you actually have a state for context that you have to pass around. So you have the same exact program here, but now we're saying, all right, we manually are having to pass a state around A. B, we had the functions external to that. So we can do it, but that's not quite the same thing. But I should point out that in the newer GCC stuff, you can do exactly the same. There is this concept in the GCC of nested functions. So actually what I've got here is this is much cleaner, and I've got this idea of a nested function. So this function, the scope of this function can only be referenced within inside this function, but yet inside this function, we have access to other local variables outside of it. So you can do the exact same problem that way. So I thought that was just interesting to me. So there's a couple other projects that are interesting. There's one called Elixir, which is a different language. It's not Erlang, that is compiled and runs on the Erlang runtime. I have not personally used it. It sounds exciting. I think a lot of these same concepts we talked about today would map directly to that. I think it's an attempt to use probably a nicer syntax. I've inherited a lot of Erlang code, and that's why I'm still learning that world, but that's definitely something to take a look at. Another one is Erlang, which is an example of doing the other way around. We can take the Erlang language and run that on another. Is basically this built on top of this language and these libraries and runtime is this framework for these generic ways that you would solve repeatable problems. The one that we didn't talk about that gives a huge benefit to using Erlang in the first place is this supervisory infrastructure. So there's all these built-in language facilities where you can say, let me know whether or not this process is still alive. And I can monitor that, and then you can do your own low-level logic, but they've got all this other higher-level logic where you can very quickly whip up these things and say, if this ever dies, restart it. Or if this ever dies, kills this entire process tree and restart it. Or do any other combination of logic. And you can build these highly sophisticated means of recovery, failure recovery, and adaptive healing across numbers of machines. So there are applications where the only thing you do with Erlang is that, and then you can actually call other code in other languages for other work if you wanted to. It's actually that worthwhile to go to that much trouble. A couple recommendations. On the web, this guy has his book for free, and that's where I started. It's called learnusomeerlang.com. You can actually you can buy the book, but you can just read the entire thing on his website. It's really cool. Little bit of constructive criticism. The target audience is probably newer to some of these concepts in general. So, which is probably good if you're depending on where you're coming from. But he goes into a lot of detail explaining some of these concepts. This is a little wordy for me. On the other hand, if you've programmed for a long time and you're just looking for something a little more technical to just make it easier, this recently came out. This is the second edition. This is one of the actual original authors of Erlang working the project. I would recommend this book out of the ones I've seen. The Erlang mailing list is definitely the way to go. They cooperate with you, and it's a small enough community that people look out for each other's interest, and they want to try to promote their brand name, so to speak, and they're really friendly and answering. Definitely, at least reading the mailing list if you play with it. I also put my own YouTube video on here from the Erlang factory if you would like even more geeking out about even more imaginative concepts with computers and how this stuff interrelates with each other. Please go watch that if you are interested. So we've got a few minutes. So then I thought an exercise. How would you solve some of these problems, and to imagine how well you can easily solve them in Erlang. These are kind of use cases. So, excuse me, if you imagine, let's say we had a single integer. Maybe it's the next unique number or something like that. That we needed to keep this across the entire internet and actually make an authoritative source for this. You can make that in anything, but making that in Erlang is, you have most of the problem solved already. You can just work on the logic of how you want this to work, how you want to do your elections when you have network splits and stuff like that. You can just go straight to that logic instead of actually trying to code up all this networking code and all this failover code and all this stuff, which you can still do, but I mean, that's not a performance sensitive task at all. Just do that. It's great. Save your life, The 9.9. So when you're trying to make a system that really should stay up, for the 0.99999, how do you do that? How do you actually make something that does that? Obviously Linux, right? But you need more than that. You need your logic and your application code. Erlang is that's where it's for. I mean, it's made for, that was the original problem trying to solve telecom systems that do not ever break. And so another one that we use it for, where I work, is we use it for a lot of things, but let's say you've got just a web browser type UI application, and we want to hit our backend RESTful endpoints are going to hit something, and that needs to be able to do some work. Might be work that takes a few seconds, might be work that takes, let's say, an hour or a few minutes. And we might want to do some things. We want to monitor that. We want to have some kind of control over that. We want to do some feedback with that. I know that I understand that there's some facilities in Rails that let you do this kind of stuff. But let's say you wanted to do this with multiple nodes, and let's say you want to use, some other infrastructure, Erlang. And then the big one, or a big one, one of the big ones, watchdog logic. So like we just alluded to with the supervisory infrastructure. this concept of, let's just say you want to have a program that stays up and running. It can be complicated. A lot of little details. System D, though, it's pretty neat. I would definitely do that. Okay, so any System D is to have some merged themes here from this conference. To me, one of the ones like a lot of the things that you would try to do with Erlang supervisory infrastructure are being done with System D. And so you don't get as complicated logic. I don't know, I need to look at it some more. But that is if you're back to one machine, or even if you go to like CoreOS and you can use multiple machines, I think they have some wrapper. That's interesting. So that would be a more modern approach if you're on Linux. It's just something to think about. That I've been thinking about. So I can see that just the disdain for System D. I was so anti-System D until recently. And I'm really excited about trying it for some things, actually. Anyway, so comments, questions? Yes?
So another thing that uses Erlang that sounds well is CouchDB.
Yes, that's true. I forgot.
It's another NoSQL database.
That's a good one.
Also, a lot of the Java servers in Java D, the largest deployed in Java D networks or Erlang.
Those are
Facebook's chat services all run on Erlang in the background.
those are excellent examples. So the first comment was about CouchDB being an excellent another example of something cool that is built with Erlang, and the other comment was the JabberD, which was the I forget what it was originally written in. Was it always in Erlang to begin with?
What's the E?
Oh, okay. It was always in Erlang. I didn't know, but that's another famous example of it. And then the Facebook chat server is already. So you're writing a chat server is like a fun exercise just to do it. I mean, that's like, you could be the second or third day you're playing with this, you can make your own chat server. It's just like, I mean, it's for academic teaching or just experimenting or learning or playing around. This is fun. I mean, this is like a chemistry set that you can just blow stuff up with. It's fun. It's a really fun thing. I mean, I wish a long, long time ago when I was learning to do sockets, some of the stuff the hard way, if I'd had this, I probably would never even have learned it. It would have spoiled me. So, anyway. Okay, any other? Yes?
Do you have any wisdom when it comes to distribution? So, I got this product working, now I got to get to my customer, and they just want to run it, sell things.
Yes. So, So the question was about distributing Erlang applications to an end customer. So that has not been one of the strong spots. And so some of these other things that we talked about, like React, for example, that's one of the problems you get into is, how do I make this work? But it's actually solvable in a few ways. One of them is just try to make your code work well enough to where you can just use your Linux distributions packages of it, and of Erlang itself, and then just try to make it work with the different ones. There's limited reasons to actually make it work on specific versions of Erlang. That would just be in general. But there's this facility they call the release facility. So you can, using that OTP framework, where you can make these text files to sort of explain what the dependencies are that in your Erlang application. You run through this procedure, and it creates what's called a boot script and some other things. And so you go all the way through and it actually can make a directory with everything you need in it, all the Erlang dependencies, and it is redeployable in that sense. But then if you're actually talking about, I have a customer and I've written something for him and I would deploy it. At this point in time, I would seriously take a look at some of these more cutting edge delivery technologies like a Docker or a container, or something like that. I mean, I think that if you're delivering a finished end result binary, I would investigate some. These are just with anything in general. These are some kind of new ways of looking at things. But if you're like, nah, I've made it more complex, but I actually think that would simplify it. Actually. No. Static linking is the devil's. Don't ever, no static linking. No one ever wants to. There is no foolproof. There's no foolproof, and static linking is deceptive. You know. So. Yes, for example. So like, yeah, that hits close to home. You know, that's just one. So, but you know, the containerized deployment approach, in a sense, is still gives you those restrictions of static linking. So you still need to do updates. But as far as I don't know, if I was in a situation today where I was actually deploying like a finished binary to a customer, I would find some way to deliver it as that, because there's just too many things you don't control. And if you want something like idiot proof, that would, you know, either or just a VM even at that point. But you know, if you have a more technical customer and you're delivering them source code, that's different. Then the solution is you deliver them source code. That's the whole point. So maybe that wasn't the best answer, but yes.
One of the advantages of using OTP and Rebar is that it allows you to do, it provides a lot of structure and you can script around it. Plus it also makes things like hot swapping code, new code, perfect. So if you stick with those standards, it's a little bit of extra effort which you have to do the configuration files to specify to define your application. But if you do that, that means that when you actually deploy upgrades to your customer, they don't have to stop and restart their service. They just say new version, and when I'll let you explain how it works.
Yeah.
Messages.
So the comment was, there is this other external tool called Rebar, which is a general purpose Erlang build system, which does several things for you. One of which allows you to have an Erlang build system. Another one is that it is a wrapper around that release infrastructure we were talking about, where it lets you distribute things with all the dependencies with it. And the other one it lets you do is there's this other feature we didn't talk about that Erlang has, where you can do hot code loading. So you can actually set things up in such a way to where you say, excuse me, similar to the way you would do with kernel module loading. And actually say, all right, we have a piece of code that's in use, it's live, and I'd like to send an updated version of that code in line. And as soon as all the older users of that no longer are using it, it just goes away. But all the new users, new requests go to the new code. And to do that, it is possible. You have to obviously make the logic of the program code itself still work, which is the hardest part. But other than that, there's some procedures you have to follow. And the Rebar infrastructure facilitates doing that easier. All right, okay, one more, yeah. So yes, there have been at least two, keep in mind, I'm not the world's biggest Erlang historical expert because I've been on this for about 10 months now, what did you ask me? Oh yeah, native code to actually take Erlang code and compile that into a native machine code. And those efforts have actually been abandoned as far as I can tell. They're still sort of there. There was another one of them was just more of just-in-time compilation, where we still have, that code is still there. I don't believe it actually gets used. It's kind of a side discussion on why just-in-time compilation as a school of thought, I think, is played out. But, you know, the Beam stuff is very fast. If you need something faster, just go to regular C. You know, I mean, at that point, use the right tool for the job. So there is no such thing that's like, this is the thing that solves every problem all the time. Anybody who tells you that is ignorant. Okay. Now, there are ways that you can do stuff all the time, but it's suboptimal, or it's quick use trade-off. So yes, go ahead.
Since you mentioned using C, things you need high efficiency for.
That's just one example, yeah.
You could write C code or code in pretty much any other language, and you can integrate that into Erlang, and in such a way that if your C code fails, then it passes that message back to Erlang, and then Erlang supervisors the tree and everything else will then solve those problems for you.
Yes. So the comment was that number one, that and you can interact with Erlang in all these other languages, almost any other language, in many different ways. One way, is, like I said, was using the distribution protocol natively. There's other ways where you can just spawn out of the processes and route them to ports and stuff. But in the case of C code, for example, that's actually at our office. That's one of the things we have now. So you can put C code in process I got 1 minute in process with the beam, and there's some efficiency to be gained because you don't have to copy messages. On the other hand, if you crash or anything, you bring down the whole beam, and that's part of the whole reason why you want Erlang is for the rock solid. So you can take like your C program, separate process to the side, and you can still use these monitoring facilities to where if your C program crashes, the Erlang supervisory logic is well aware of that, and you can act accordingly. And so it is very well designed with the intention that you are going to be probably using heterogeneous technology. It does a very good job of gluing these. It's a good glue language. It glues these things together very well. So I think we're out of time, and I will be here for a little bit before I have to run to the airport. But thank you very much for your attention and for coming out this early time slot. And thank our sponsors and everyone else. Thank you so much.
Your customers rely on your website or application. If it's slow or non-responsive, it infuriates your users and costs you money. Keeping your business-critical systems humming along requires insight into what they're doing. Your system metrics tell stories that can reveal performance bottlenecks, resource limitations, and other problems. But how do you keep an eye on all of your system's performance metrics in real time and record this data for later analysis? Enter Longview, the new way to see what's really going on under the hood. The Longview dashboard lets you visualize the status of all your systems, providing you with a bird's-eye view of your entire fleet. You can sort by CPU, memory, swap, processes load, and network usage. Click a specific system to access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding Longview to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to Longview. Then the graphs start rolling. Use Longview to gain visibility into your servers, so when your website or app heats up, it stays up.